Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. High above Earth's surface, in the seemingly infinite expanse of space, humanity has created an invisible but growing catastrophe. Orbital debris, fragments of defunct satellites, spent rocket stages, and collision remnants, now threatens every spacecraft we launch and every astronaut we send beyond our atmosphere. The numbers are staggering. NASA's Orbital Debris Program office tracks approximately 34,000 objects, larger than 10 centimeters in diameter, currently orbiting Earth. But this represents only the tip of the iceberg. Scientists estimate that over 130 million pieces between 1 millimeter and 1 centimeter exist in orbit, while debris fragments smaller than 1 millimeter number in the trillions. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The genesis of this crisis traces back to October 4, 1957, when the Soviet Union launched Sputnik 1. Since then, over 6,000 launches have deposited more than 56,000 tracked objects into Earth's orbital environment. While many have naturally decayed and burned up in the atmosphere, thousands remain, creating an increasingly congested and dangerous environment. The most concerning aspect of orbital debris lies in its velocity. Objects in low Earth orbit travel at approximately 17,500 miles per hour, nearly 10 times faster than a bullet. At these velocities, even paint flecks become projectiles capable of damaging spacecraft windows and solar panels. A collision with a piece of debris just 10 centimeters across could completely destroy a satellite or crewed spacecraft. This scenario becomes even more alarming when we consider the Kessler syndrome, first proposed by NASA scientist Donald Kessler in 1978. This theoretical cascade effect describes how the density of objects in orbit could reach a tipping point where collisions generate more debris, which causes more collisions, creating an exponential growth in space. Junk. Such a cascade could render entire orbital regions unusable for decades or even centuries. Recent events have demonstrated this isn't merely theoretical. In 2009, the active commercial satellite Iridium-33 collided with the defunct Russian military satellite Cosmos 2251, creating over 2,000 trackable pieces of debris. Similarly, China's anti-satellite test in 2007, which destroyed their own Fengyun 1C weather satellite, generated more than 3,500 pieces of trackable debris that continue to pose risks today. The International Space Station regularly performs debris avoidance maneuvers, sometimes requiring astronauts to shelter in their Soyuz spacecraft as protection against potential impacts. Commercial satellite operators like SpaceX have had to maneuver their Starlink constellations to avoid collision threats, demonstrating how debris affects both government and private space operations. The economic implications are substantial. The European Space Agency estimates that the annual cost of debris-related damage and avoidance maneuvers exceeds 100 million euros. Insurance costs for satellite launches continue to rise as the debris environment becomes more hazardous, potentially pricing smaller nations and organizations out of space access entirely. Current mitigation efforts focus primarily on tracking and avoidance. The U.S. Space Surveillance Network monitors objects larger than 10 centimeters and provides collision warnings to satellite operators. However, this reactive approach only addresses the symptoms, not the underlying problem of accumulating debris. International guidelines recommend that spacecraft operators dispose of their vehicles within 25 years of mission completion, either through controlled re-entry or movement to graveyard orbits. Yet compliance remains voluntary and inconsistent, while these guidelines do nothing to address the massive amount of debris already in orbit. The challenge extends beyond technology to international cooperation. Space debris affects all spacefaring nations equally, regardless of who created it. A piece of debris generated by one country can threaten spacecraft from any other nation, making this truly a global problem requiring coordinated solutions. As we stand at this critical juncture in human space exploration, with ambitious plans for lunar bases, Mars missions, and expanding satellite constellations addressing orbital, debris has become not just an environmental necessity, but an existential requirement for our continued presence in space. The solution may lie in a revolutionary concept, transforming our space junk problem into a space resource opportunity through orbital debris recycling. To effectively address the orbital debris crisis, we must first understand the complex physics and diverse nature of the objects cluttering our orbital highways. Orbital debris exists in a three-dimensional environment governed by precise mathematical laws where every fragment follows predictable trajectories determined by gravitational forces, atmospheric drag, and solar radiation pressure. Debris populations vary dramatically based on altitude. In low Earth orbit, between 160 and 2,000 kilometers above Earth's surface, atmospheric drag gradually pulls objects downward, causing them to burn up during re-entry within years or decades. However, at higher altitudes in geostationary orbit, 35,786 kilometers above the equator, debris can persist for millions of years without natural decay. The composition of orbital debris reflects humanity's six-decade history of space exploration. Intact defunct satellites constitute the largest individual objects, ranging from small CubeSats, weighing just kilograms, to massive communication satellites exceeding 6 tons. These dead satellites continue orbiting as potential collision hazards, their solar panels and antennas, creating complex shapes that complicate tracking and removal efforts. Spent rocket stages represent another significant category. Upper stages from launch vehicles like the Delta, Atlas, and Ariane rockets remain in orbit after delivering their payloads. Many of these stages still contain residual fuel, creating explosion risks that can generate thousands of additional debris fragments. The phenomenon of delayed fragmentation has been observed in over 200 cases, where apparently inert objects suddenly break apart years or decades after launch. Mission-related debris includes items lost during spacewalks, such as tools, gloves, and camera lenses. While individually small, these objects travel at the same tremendous velocities as larger debris. In 1965, astronaut Edward White lost a glove during the first American spacewalk, which orbited Earth for a month before burning up in the atmosphere. Collision fragments constitute the fastest-growing debris category. When two objects collide in orbit, they shatter into countless pieces, each following its own orbital path. The collision between Iridium-33 and Cosmos 225. One created debris with orbital periods ranging from 90 minutes to several hours, meaning fragments spread across multiple orbital planes over time. Paint flecks might seem insignificant, but they represent a serious threat to spacecraft operations. Thermal cycling in space causes paint to expand and contract repeatedly, eventually flaking off surfaces. These microscopic particles, traveling at hypervelocity speeds, can pit spacecraft windows and degrade solar panel efficiency. The Hubble Space Telescope has required multiple servicing missions, partly due to paint fleck impacts affecting its precision instruments. Tracking orbital debris presents enormous technical challenges. Ground-based radar systems can detect objects as small as 5 centimeters in low Earth orbit, but their effectiveness diminishes with altitude and object size. The U.S. Space Surveillance Network operates 29 sensors worldwide, including powerful radars like the Space Fence system in the Marshall Islands, which can track objects as small as 2 centimeters. Optical telescopes complement radar tracking, particularly for objects in higher orbits where radar performance decreases. However, optical tracking depends on favorable lighting conditions and clear weather, limiting continuous monitoring capabilities. The challenge intensifies when considering that debris objects tumble unpredictably, causing their radar cross-sections to vary dramatically. Orbital mechanics complicate debris behavior further. Objects in elliptical orbits experience varying velocities, with highest speeds occurring at perigee, the closest approach to Earth. This creates complex interaction patterns where debris from different orbital inclinations can intersect at multiple points, making collision probability calculations computationally intensive. Solar activity affects debris behavior through atmospheric expansion. During solar maximum periods, increased solar radiation heats Earth's upper atmosphere, causing it to expand upward. This increases atmospheric drag on low-orbiting debris, accelerating their orbital decay, but also making their trajectories less predictable. The debris environment exhibits statistical clustering, with certain orbital regions containing higher debris concentrations. The 800 to 900 kilometer altitude band contains particularly dense debris populations from past satellite breakups, creating ongoing collision risks that could trigger cascading failures. Understanding these complex dynamics reveals why traditional cleanup approaches have proven insufficient. Simply removing large objects doesn't address the exponentially larger population of smaller fragments, while the three-dimensional nature of orbital mechanics means debris spreads across vast volumes of space over time. This complexity has driven scientists and engineers toward innovative solutions that don't just remove debris but transform it into valuable resources. The fight against orbital debris has sparked remarkable innovation in space technology, with engineers developing increasingly sophisticated methods to track, capture, and remove dangerous objects from Earth's orbital environment. These efforts represent humanity's first serious attempt at large-scale environmental remediation beyond our planet's atmosphere. Active debris removal missions have moved from theoretical concepts to operational reality. The European Space Agency's ClearSpace 1 mission, scheduled for launch in 2026, will demonstrate autonomous rendezvous and capture techniques by targeting Vespa, a Vega rocket upper stage weighing 112 kilograms. This mission will validate critical technologies, including proximity operations, robotic capture mechanisms, and controlled deorbit procedures. Japan's Aerospace Exploration Agency has pioneered electrodynamic tether technology through their EDT demonstrations. These systems deploy long conductive cables that interact with Earth's magnetic field, generating drag forces that accelerate orbital decay. While early experiments faced technical challenges, refined versions show promise for deorbiting large objects without requiring complex rendezvous maneuvers. Robotic capture systems employ various approaches to secure debris targets. Harpoon, systems developed by Airbus Defence and Space, fire barbed projectiles into debris objects, providing secure attachment points for subsequent towing operations. Net capture systems deploy large mesh structures to ensnare tumbling debris, particularly effective for objects with complex geometries like defunct satellites with extended solar panels. Ground-based laser systems represent a non-contact debris removal approach. The proposed Orion laser system would use powerful ground-based lasers to ablate material from debris surfaces, creating thrust that alters orbital trajectories. While still experimental, this technology could potentially affect thousands of small debris objects simultaneously without requiring expensive spacecraft missions. International cooperation has become essential for debris mitigation efforts. The Interagency Space Debris Coordination Committee, established in 1993, brings together space agencies from major spacefaring nations to develop common guidelines and share tracking data. This collaboration has produced standardized debris mitigation practices and improved orbital conjunction analysis capabilities. Space traffic management systems have evolved dramatically in recent years. The U.S. Space Force's 18th Space Control Squadron provides collision warnings to satellite operators worldwide, analyzing over 500,000 potential conjunctions daily. Their systems can predict close approaches days in advance, allowing operators to perform avoidance maneuvers when necessary. Commercial space surveillance companies have emerged as crucial partners in debris tracking. Companies like Leolabs operate networks of ground-based radars specifically designed for small debris detection, providing higher resolution tracking data than traditional military systems. Their commercial approach has accelerated technological development and reduced costs. For debris monitoring services, atmospheric drag enhancement techniques offer passive debris removal capabilities. The European Space Agency's drag augmentation systems attach to satellites before launch, deploying large surface areas at mission end to increase atmospheric drag and accelerate orbital decay. These systems can reduce deorbit times from decades to months for satellites in low Earth orbit. Mission design requirements have evolved to incorporate debris mitigation from the earliest planning stages. New satellites must demonstrate 25-year disposal compliance, proving they can either deorbit safely or move to graveyard orbits beyond operational altitudes. Propulsion systems must retain sufficient fuel reserves for end-of-life maneuvers, fundamentally changing spacecraft design philosophy. Collision avoidance algorithms have become increasingly sophisticated, incorporating probability analysis and Monte Carlo simulations to assess conjunction risks. Modern systems consider uncertainty ellipses around predicted object positions, calculating collision probabilities that account for tracking errors and orbital perturbations. When probabilities exceed predetermined thresholds, automated systems generate avoidance recommendations. Small satellite disposal techniques address the growing CubeSat population through innovative approaches. Drag sails deploy from tiny satellites to increase atmospheric drag, while some missions incorporate biodegradable components that naturally degrade in the space environment. These solutions must balance effectiveness with severe mass and volume constraints inherent to small satellite platforms. Despite these technological advances, current cleanup capabilities address only a fraction of the existing debris population. Most active removal missions target single large objects, while millions of smaller fragments remain unaddressed. The economics of debris removal remain challenging, with missions costing tens of millions of dollars to remove individual objects. The limitations of conventional cleanup approaches have motivated researchers to explore more ambitious concepts that could address debris populations at scale while generating economic returns. Rather than simply disposing of orbital debris, emerging technologies propose transforming space junk into valuable resources through sophisticated recycling processes, potentially revolutionizing both debris mitigation and space resource utilization. The concept of orbital debris recycling represents a paradigm shift from waste disposal to resource recovery, transforming humanity's greatest space challenge into a potential economic opportunity. This revolutionary approach could simultaneously clean Earth's orbital environment while providing raw materials for expanding space infrastructure. In-orbit manufacturing platforms form the foundation of debris recycling concepts. These sophisticated facilities would process captured debris through automated systems capable of sorting, melting, and reshaping materials in the microgravity environment. Unlike terrestrial recycling, orbital processing eliminates gravitational constraints, enabling the creation of larger, more complex structures impossible to manufacture on Earth's surface. Material composition analysis reveals the tremendous value locked within orbital debris. Aluminum, titanium, and specialized alloys used in spacecraft construction are extraordinarily expensive to launch from Earth, costing thousands of dollars per kilogram. Defunct satellites contain high-grade materials, including rare earth elements in electronic components, precious metals in circuit boards, and advanced composites in structural elements. Robotic capture and processing systems must overcome unique challenges in the space environment. Without atmospheric pressure, traditional welding techniques require specialized equipment, while the absence of gravity complicates material handling and containment. Proposed solutions include electron beam welding systems that operate in vacuum conditions and magnetic containment systems for processing molten metals. The Archinaut demonstration missions have validated key in-space manufacturing technologies. Developed by Made in Space Incorporated, these platforms can extrude and assemble structural elements in orbit, proving that complex manufacturing operations are feasible beyond Earth's atmosphere. Future versions could process recycled materials from debris into new spacecraft components or infrastructure elements. Automated sorting mechanisms represent critical technology requirements for debris recycling operations. Advanced computer vision systems must identify different materials within tumbling debris objects, while robotic manipulators separate components for specialized processing. Machine learning algorithms trained on debris databases could optimize sorting efficiency, and identify valuable materials within complex assemblies. Solar-powered processing systems offer sustainable energy sources for orbital recycling operations. Large solar arrays deployed from recycling platforms could provide the substantial electrical power required for material melting and reshaping processes. Concentrated solar systems using mirrors or lenses could achieve the high temperatures necessary for metal processing without requiring massive electrical power systems. Economic modeling suggests orbital debris recycling could become financially viable within decades. Launch costs for raw materials to orbit currently exceed $10,000 per kilogram, while processed materials in orbit could command premium prices for space construction projects. A single large defunct satellite might contain materials worth millions of dollars if processed and reused in orbit. Additive manufacturing integration enables the production of complex components from recycled materials. Three-dimensional printing technologies adapted for space environments could transform processed debris into replacement parts for operating satellites, structural elements for space stations, or components for deep space missions. This capability would reduce dependence on Earth-based supply chains for space operations. Modular processing systems could address different debris categories through specialized equipment. Smaller modules might focus on electronic component recovery, extracting valuable rare earth elements and precious metals from circuit boards. Larger modules could process structural components, melting aluminum and titanium for reformation into new shapes and configurations. Autonomous operation capabilities are essential for economic viability of orbital recycling systems. These platforms must function for years without human intervention, making complex decisions about target selection, capture procedures, and processing priorities. Artificial intelligence systems would optimize operations based on debris availability, material prices, and customer demand for specific products. Contamination management presents unique challenges in the space environment. Debris objects may contain hazardous materials like hydrazine fuel or radioactive power sources that require specialized handling procedures. Processing systems must incorporate containment technologies to prevent contamination of valuable materials or surrounding space environment. Quality control mechanisms ensure recycled materials meet specifications for space applications. Non-destructive testing equipment would verify material properties and structural integrity before products leave processing facilities. Automated inspection systems using X-ray and ultrasonic technologies could detect flaws invisible to optical sensors. Transportation. Logistics involve moving processed materials to customers throughout the solar system. Orbital tugs could deliver recycled components to space stations, while larger transport vehicles might carry materials to lunar bases or Mars colonies. The development of efficient space transportation networks becomes crucial for realizing the full economic potential of orbital recycling. The integration of debris recycling with space manufacturing could create entirely new industries beyond Earth's atmosphere. Rather than viewing orbital debris as waste requiring expensive disposal, this technology transforms space junk into the foundation for sustainable space development, supporting humanity's expansion throughout the solar system. The transformation of orbital debris from environmental hazard to economic resource could fundamentally reshape humanity's relationship with space, creating sustainable pathways for expansion beyond Earth, while establishing the foundation for a thriving orbital economy that benefits all spacefaring nations. Long-term sustainability models envision orbital recycling facilities as cornerstones of space infrastructure development. These platforms would process not only existing debris, but also end-of-life satellites and spacecraft, creating closed-loop systems where nothing becomes waste. Materials would continuously cycle through multiple uses, supporting construction of massive solar power stations, space habitats, and interplanetary vessels without depleting Earth's resources. Regulatory frameworks must evolve to accommodate orbital recycling operations while maintaining space safety and security. Current space law, primarily based on the 1967 Outer Space Treaty, lacks specific provisions for commercial, Debris processing and resource extraction. New international agreements will need to address ownership rights, liability issues, and environmental protection standards for orbital recycling activities. The establishment of orbital recycling zones could organize space activities more efficiently. Designated regions in stable orbits would serve as collection and processing centers, where debris naturally accumulates through gravitational perturbations and atmospheric drag effects. These zones would become industrial centers of space, supporting infrastructure including power generation, communication networks, and transportation hubs. Commercial opportunities extend far beyond simple material recovery. Specialized recycling companies could offer debris removal services to satellite operators, generating revenue while cleaning orbital space. Insurance companies might mandate debris recycling for high-value satellites, creating guaranteed markets for recycling services. Space tourism companies could incorporate orbital recycling facilities as destinations, allowing visitors to witness space environmental restoration efforts. Technological spin-offs from orbital recycling development will benefit terrestrial applications. Advanced robotic systems designed for debris capture could improve automated manufacturing on Earth. Materials processing techniques developed for zero-gravity environments might enable new terrestrial recycling capabilities. Solar concentration. Systems for orbital metal processing could enhance Earth-based solar power generation. Educational and workforce development programs will become essential as the orbital recycling industry matures. Universities could establish space recycling engineering programs, while technical schools might train technicians for remote operation of orbital facilities. International cooperation in education could ensure developing nations participate in the growing space economy rather than being excluded by technological barriers. Environmental monitoring systems will track the effectiveness of orbital recycling efforts. Continuous measurement of debris populations in different orbital regions would quantify cleanup progress and identify emerging debris threats. Automated systems could adjust recycling priorities based on real-time collision risk assessments, optimizing both safety and economic returns. Financial mechanisms must support the substantial initial investments required for orbital recycling infrastructure. Space development banks could provide low-interest loans for recycling facility construction, while international development funds might subsidize debris cleanup efforts. Carbon credit systems could recognize orbital recycling as environmental remediation, providing additional revenue streams for recycling operators. The integration of orbital recycling with lunar and Martian development creates synergistic opportunities. Recycled materials from Earth orbit could supply construction materials for lunar bases, reducing launch costs for space settlement. Advanced recycling technologies tested in Earth orbit could be adapted for processing resources on other worlds, supporting truly sustainable space colonization. Space archaeology considerations will preserve historically significant artifacts while maximizing recycling efficiency. Early satellites like Vanguard 1, still orbiting after more than 60 years, represent irreplaceable cultural heritage that must be protected even as surrounding debris is processed. Careful cataloging and preservation efforts will balance historical conservation with practical cleanup needs. Quality assurance standards for recycled space materials will ensure reliability and safety. International certification programs could establish quality grades for recycled metals, composites, and electronic components. Standardized testing procedures would verify that recycled materials meet stringent requirements for spacecraft construction and space habitat development. The emergence of orbital recycling could democratize space access by reducing costs for spacecraft construction and operation. Smaller nations and private organizations could afford space missions using recycled materials, expanding global participation in space exploration. This democratization effect could accelerate scientific discovery and technological innovation through increased diversity in space activities. As we stand on the threshold of becoming a truly spacefaring civilization, orbital debris recycling represents more than environmental remediation. It embodies humanity's evolution towards sustainable space development. By transforming our orbital waste into valuable resources, we not only clean up the mistakes of the past, but create the foundation for a prosperous future among the stars, ensuring that space remains accessible for generations to come while supporting humanity's greatest adventure, the exploration and settlement of the cosmos.